Good morning, everyone. This is what yesterday we had completed, right? Now, in today's session, we will discuss about the FTIR instrument. Spectroscopy, we have talked about UV visible spectrophotometer, right? Now, here it is about the details of FTIR. Now, what is FTIR? How it works? All these things we will do. Now, when it comes to FTIR, just ask yourself how atoms are connected together, which bonds are single, double, or triple, what functional groups exist in the molecule, if we have a specific stereoisomer present. So, in short, the organic structure is on account of the atoms, how they are linked to each other, what kind of structure gets developed by joining these atoms in a particular form, what functional groups get attached, so that organic structure is going to be responsible for its functionality. So it is essential to determine the organic structure of molecules. So if we want to know that, we have to have some methods to analyze the molecule and try to answer these questions, right? So is it possible? Yes. The instrumental methods which are important in determining the structure of a molecule or a sample analyte, whatever you refer to it, but ultimately it's a molecule or it is a substance, complex, right, compound. We have to take help of certain instruments. What are those instruments? Nuclear magnetic resonance, then infrared spectroscopy, mass spectroscopy, and ultraviolet spectroscopy. So in yesterday's lecture, we have discussed about UV visible spectroscopy to details, right? So when it comes to determining the structure of molecules or compounds, then how is your ultraviolet spectroscopy important? So promotion of electrons to higher energy level occurs when we irradiate them. That is when we pass the light or through the sample, right? So the presence of conjugated pi systems and the presence of double and triple bonds can be identified. Now, in yesterday's lecture, we have talked about how UV spectroscopy can be utilized to find out concentration concentration of molecules like DNA, RNA, protein, which absorb in the range of UV region. Also, can we determine the structural variation of these molecules. For example, whether the DNA is present in double stranded form, is it melting, is it single strand, how to determine temperature of TM value. So experimental method to determine TM value includes use of UV spectrophotometer, which is going to analyze the DNA at every interval and going to tell us about how much amount of DNA is intact, how much has molten, because as DNA melts, absorbance increases. So these are certain examples we had discussed. Protein estimation yesterday we had discussed using UV. So in addition to that, concentration, purity, structural morphology, the structural features of the molecule, are we able to talk about the other facets of structure, right? As we said earlier, ki how the molecules are arranged, what functional groups are present, can we find out using spectrophotometer. So using UV spectrophotometry, presence of conjugated pi bonds and the presence of double and triple bonds can be talked about. Now another is nuclear magnetic resonance. We will talk about it little later. Infrared spectroscopy, that is today's topic. So here let's know in one line about how it works. Triggering molecular vibrations to irradiation with infrared light. It will provide information about presence or absence of certain functional groups. So these two lines tell us that yes, you are going to take the sample, you are going to irradiate it with samples light source, right? As in colorimeter, you keep your cuvette in the instrument, the sample holder is cuvette, sample is in it, you keep it in the machine and you start the machine, and you allow the light to fall on it. You change the filter, the selected filter select the specific band of wavelength and it passes to the sample. So that is irradiation. So here also you are going to keep your sample in front of the light source, but the light source should be which is going to generate infrared rays. Okay, and then it will help us to understand presence of functional groups. So what is the basis of this analysis? It is molecular vibrations. Now when we talk about infrared spectroscopy, it is a technique that is used for molecular identification. And how it works? It works by measurement of infrared spectrum of a substance. Now it is found to be of different types when it comes to infrared also. FTIR is one of those, Fourier transfer infrared frequencies, which is going to allow simultaneous measurement of entire spectral range and analysis of sample, so which is not possible otherwise. So, because we are talking with reference to molecules, infrared spectroscopy is also referred as molecular spectroscopy because we are determining information about molecular structure or mixture of molecules or what kind of functional groups are attached to it. So, infrared is going to give us insights about structure of the molecule, the functional groups present, and how it varies when you compare two different molecules. Say variation with a single functional group or a single hydrogen bond or a single type of bond, that is whether it is C double bond O or it is CHO or COOH or CO, keto, aldehyde, alcohol, CO and H. All these three atoms they come together in this, but different types of bonds are there between these three, right? When we say keto, C double bond O. When we say aldehyde, CHO. But when it is CH and O, three atoms you consider in a different arrangement, COH, it becomes alcohol, right? So to get this kind of information, we take help of IR spectroscopy. So it talks about how the bonds between the atoms of a molecule, they will absorb energy. So when you pass the light energy, that energy is absorbed by the molecule, and which is not absorbed is transmitted. But the absorbed energy is going to cause vibrations, right, in the atoms of the molecule. And this energy is going to be important to cause motion in these bonds, which is going to be specific because it is going to be determined by the atoms present in the type of bond, the arrangement of those atoms within a molecule, bond angle, and so on. So detailed insight about the structure of a molecule can be obtained by exposing your sample to IR and spectroscopic measurements based on that. So when I say uh, IR spectroscopy, yes, when it comes to as a technique for analysis, it is very simple, quick, and uh, economically also very approachable, very cheap method to say. So that is one thing. Second is you can analyze the structure of molecules, whether whatever may be the form of the analyte, may it be solid, may it be liquid or gases. Of course, the methods are going to vary when we are going to apply the sample to the instrument. If it is gas, how do we go? It is liquid, how do we go? And if it is solid, how do we go? Will differ. But yes, you can analyze all different types of substances using this. Now, just as I mentioned earlier, organic compound contains mainly C, H, and O. Of course, nitrogen, phosphate, etc. also are present, but the major components are CHO. And the arrangement of CHO with each other is going to be of different forms. And you need to differentiate, then only you will be able to talk about what the nature of the molecule is. For example, just glucose, if you talk, and it is aldehyde form. But if you talk about the keto form of sugars, it becomes C double bond O. So we need to identify these because these small things, arrangement of atoms within a molecule and type of bond, are going to decide the functionality, the reactivity, the nature, the property, the characteristic of the molecule. So this all can be viewed through or overviewed through, I will say, FTIR, because no one single technique is enough to characterize any molecule to the complete details. So here we are going to know about the arrangement of atoms within a molecule and the type of bonds, the type of functional groups, etc. Now when I say IR, It is in the three ranges, right? Near IR, mid IR, FIR, Fourier transform, and far IR also is there, which is not mentioned in this case. Now, the molecules are going to absorb in these range. So when I see the spectrum of light, we talk about visible light, UV light ranges. So here, the wavelength I'm talking here, it is about uh, towards the left side of your visible range, right? And phi IR is to the extreme other end of it. So the wave frequencies, wave number, and photon energy are the three components that we have to remember. Wave frequency is denoted by a letter small v, wave number by v bar like a vector, and photon energy hc by lambda. So these are the three concepts which are going to be applicable to any atom within a molecule, the bonds to it, and vibrational energy can be calculated based on that. So NIR, that is near infrared, mid infrared, and FIR. That is how we have. So if you see the range specifically, it is 4000 to 400 is mid IR. Then you have IR range which is spanning 400 to 4000. In between, uh, uh, generally when you are going with biological molecules, this range is scanned over 400 to 4000. It is not that a single wavelength is chosen and you keep it and take the absorbance. Generally, entire scanning is done over the range 400 to 4000 to get insight about the functional groups attached or type of bond present in the molecule. How it goes, we will try to understand. Now, this is the general uh, s- schematic representation about the instrument. So, this is the light source, this is the monochromator, right? This is the splitter, right? Then the sample, and then you have your detectors and the recorder system, which is really very same to any other type of spectrophotometer. Where it differs with the light source, right? So light source, which is going to be specific for IR, is again going to be what works in near IR range, what works in mid IR range, and what works in far IR range. As I said, near IR is 4000 to 14,290. So for that, tungsten filament, nichrome wire, or rhodium wire are commonly used. When it is middle region, that is between 666 to 4000, where generally we work with reference to biological molecules. Now that is going to be uh, a special light source which is called as nurse glower or glober source. These are used. What are they? We will learn. Now, for IR, mercury arc lamp or carbon dioxide laser, they are used as light source. Right. Now, as for any other spectroscopic method, whatever light is generated by the light source, the entire volume need not be allowed to enter the sample. So you are going to select the quantity of the photon or the light energy. So you have the entrance slit. We have talked about it in yesterday's lecture to the details. Entrance slit, exit slits, the pore or the distance or the diameter of the slit, the width of the slit, all these things are very crucial to get correct analysis using spectrophotometers. So you are going to have light source, then you are going to have slit, then you are going to have monochromator. In yesterday's lecture we have talked about monochromator design, which includes prisms, which includes diffraction gratings and mirrors of different types, collimating lenses, then focusing lenses, then plane mirrors, etc. All this we have talked in yesterday's lecture. So such monochromator is also present here. Then here is a sample source, right? Sample cell that is shown right here, and then splitter, detectors, and recorders. So when you are going to irradiate your sample with IR radiations, the molecules of a chemical substance, they will absorb this energy, and on account of the energy they will vibrate, right? And the rate of vibration is going to be different for each type of uh, bond, each type of atoms which are involved in the bond formation. So it is going to give you different rates of vibration. And of course, when these vibrations are generated, that can be understood by the amount of light absorbed by the molecule. So close packed absorption bands will get generated, which are called as IR absorption spectra. Right. So it is going to extend over a wide range of wavelength. It is spectra. It is not a single wavelength. Mind well. Again, I'm insisting that lambda, when you are talking about lambda max, that concept we have learned. Here, lambda of absorbance, yes, for specific functional groups, you may hit a particular wavelength. We will take an example in the next slides. But generally, because it is a complete molecule, you will get a kind of IR absorption spectra, a wide range of wavelength that is going to be absorbed. So there are different bonds, as we know. So these will be represented by different bands. What band? Wavelength band, right? So, and that band will correspond to a specific functional group, or it will correspond to the bond present in the chemical structure. So, in one word to say, the IR spectra, absorption spectra, will give you a chemical fingerprint of a substance for its identification. Now, what kind of sample holder shall we use? In UV visible, we have seen if you are working in the visible range, we use glass cuvettes. If you are using in the UV range, you need to use quartz cuvettes, right? But when we are going with IR, neither quartz nor glass is sufficiently transparent for the IR light to pass through, because the radiations above 3.5 microns, when you go, neither quartz nor glass will work. So these two types of cuvettes, that is glass cuvette or quartz cuvette, is of no use when it comes to IR. So crystals of certain halogen salts. Halogens, Bri, bromine, iodine, you remember those are the halogens. The salts of these halogens, they are used, and uh, in place of the sample holders. So, of course, quartz is employed as a material for prism construction and is used for near IR region. It strongly absorbs beyond 4 microns. Okay, uh, the reason you should know why not used, why it is not useful for IR spectroscopy. Why cannot we use glass or quartz? So, to make you understand, I have stated these sentences. Now, what is that material which is used then to hold a sample? So, crystalline NaCl as the prism material, and beyond 20 microns, NaCl absorbs strongly. So, that also cannot be used in IR. Then, what is used? Then, crystalline KBr or cerium bromide, they are commonly used. So, here are the two, KBr and cerium bromide, which are used for IR regions. Again, as per the region of IR, whether it is far IR, near IR, accordingly you will have to change. So, for a near IR region, you have to use lithium fluoride. So, whether it is lithium fluoride, whether it's potassium bromide or cerium bromide, it will change. So, in the far IR region, you are using KBr or cerium bromide, and in a near IR region, you will be using lithium bromide. Right now, let's talk about the prism, which is again a common thing to all the monochromators, whether it is IR spectro or whether it is UV visible spectro or other types of spectroscopy. Right, whenever monochromator is there, prisms and diffraction gratings are important components. We have learned in yesterday's lecture. Now, just two lines about prism. The size of the prism, the angle of the three uh, the three angles of the prism, the size of that angle, the the refractive index of the prism, all these things are going to be very important. Of course, your prism material has to be transparent, right? So there are two types of prisms which are commonly used or are known. One is refractive type, another is reflective type. Reflective type is also known as litero type of prism. So in the refractive type and reflective type, what is the difference? Let's look into it. The refractive type prism, when you talk, the light from the source through the entrance slit will fall on the collimator lens we have seen in it. Collimator, which is going to collect the initial light. The parallel radiation from the collimator are dispersed according to the wavelength, and by using another collimator, the image of the entrance slits are reformed. The required radiation in exit slit can be selected by rotating the prism. Now, these are the working details. You need not worry. You can just remember refractive type and reflective type. So, in the refractive type and reflective type, both are almost similar, only the difference is that reflective surface is present on one side of the prism. So hence the dispersed radiation get reflected and can be collected. So refraction and reflection, these are the two basic physical phenomena which are going to be working in the two types of lens systems. Now when I say the diffraction gratings, right, how do they work? This is a schematic diagram to more details. So yesterday I had told you it is very thin alumina sheet, and the surface is very much polished like super mirrors, and that polished surface is engraved with grooves you are going to erode the surface. So in 1 millimeter area there are hundreds of lines marked, right? So if you observe it through a magnifying lens, each line which is marked on the surface would appear like this. So in 1 millimeter distance there are hundreds of lines of this type. Can you imagine? So finely designed, so whenever light falls onto it, it is going to get broken down into its component wavelengths. So of course more details are there to talk about it, that is what is zero order, negative order, first order, but these are very much technical details. It is just to touch the term. I have put it here in the slide. If you are interested, you can we can talk about it in details, but for exam point of view, not more than the basic information about diffraction gratings it is to be talked about. So you are going to have per millimeter 20 grooves to 100 grooves. You have different types of the diffraction gratings, and their efficiency also is going to change with more amount of grooves or lines per unit distance, that is right? So gratings are uh, uh, made upon very uniform and reflective surface, right? So just to write about 4 5 lines about diffraction gratings in the monochromator design, this information is enough, I think. So this is the spacing of the grooves that is denoted by letter D, right? Then you have first negative order, zero order, first order, and second order. So what it is going to generate, how, when I say zero order, you see there is no colored arrows shown, right? You see the intensity of the color arrows which are getting generated. Colored arrows indicate the light which is generated from the light source is broken down into its component colors. So different colors are shown, different wavelengths, wave bands. But when you say zero order, you see only one dark gray line, right? So generally, first order is the region where we select for uh, any analysis. Now, when we talk about IR spectrophotometer, how is the sample prepared? As in UV visible colorimeter, you know you take the sample, analyte, it is suspended and solubilized in a select solvent, and the solvent should be such that it will not absorb that light wavelength which is absorbed by your sample. So selection of solvent there also is very unique. That is only what we do. But when it comes to IR, how it is going to work? Right, so there are different techniques. The first technique is referred to as mull technique. In this technique, finely ground sample, solid sample is converted to its very fine powder, and it is mixed with a mineral oil, right? So you can generate a thick paste of it which is spreaded between the IR transmitting windows, right? So you can imagine the colorimeter and its sample holder. In place of that, you have a window for keeping your sample, and the sample is in the form of a thick paste which you have prepared using the fine powder of analyte and the oil. Now, once you have pasted this sample onto the window, or the sample folder window, you can say, then it is mounted in the path of IR beam. So you have to have the holders, some kind of holders that is going to get placed in the IR path beam, and the spectrum is allowed to run, and the entire spectrum is scanned, right, from 400 to 4000, for example. You have to select, right. um, but when you use oil based preparation, there is one disadvantage, that it shows absorption maxima at these two three different wavelengths. This is 2915, 1462, etc. So this is a limitation. If your analyte also is going to be actively absorbing in this range, then it will be erroneous result. So you have to have another method. So if or remember this as the limitations of using this oil based preparation. Second is, you can use uh, uh, another technique, that is when your sample material is amorphous, right. So you have to deposit it on the surface of KBR or NaCl cell, and then how you are going to deposit. So you have to again it solubilize it in a solvent, put a drop of that solvent on the cell, let it evaporate. So once it is evaporated, the particles, the material, the solid material, maybe amorphous form, will remain on the surface of this KBR or NaCl cell. So these are the things. Of course, when I say the solvent has to get evaporated, it should be a organic solvent, right? So maybe CCl4, right? I'm sorry. Or maybe cyclohexane or benzene, acetone, which are organic solvents which evaporate easily, are used. So is the sample preparation for IR clear to you? I hope so. You are going to use either of these two methods. Now, sampling of gases, how will we do? Right? So, for sample, if it is gas, then you are going to have the gas cell, right? KBR cell, NaCl cell, you have seen. Similarly, you have a gas cell. जैसे कि कुवेट है आपका in colorimeter, here it is a cell. Here it is gas cell for gas samples. It consists of a metal bar glass cylinder of 10 centimeter, a very small cylinder of metal. So, like a capsule, you can say. It has got a appropriate window through which the gas sample is allowed to pass. Then it is going to hold that sample in it, and then you are going to uh, uh, what we say, load it on the machine. So when you see about this cylinder, the end wall of the gas is NaCl and another end is open. So from the open end, the gas will enter at a particular pressure, that is 5 to 15 millimeter Hg pressure, and then it will get impinged or impacted on NaCl. That is the other side of the gas cell is. So again, you are going to place this gas cell into the instrument, and you are going to study the absorbance and reflection pattern which is generated. If it is liquid, the liquid which is at room temperature, again you can keep it in a small rectangular cell. The cell itself is made up of NaCl or KBr or THBr or cerium bromide we have seen earlier. So it is not glass, it is not plastic, it is not cards, but it is made up of such fluoride materials, right? KBr, THBr, etc. So this is how sample for IR spectra is to be done. Now, yes, these are the details about near infrared and far infrared. What kind of detectors will you use? Right. So for near infrared lead sulfide photoconductive system is used. For mid infrared, thermopile and thermistor or pyroelectric one is used, and for far infrared, pyroelectric again is of use. At shorter wavelengths, which is about 1.2 micron, the detection method is same as that of UV visible. So in UV visible, we have to go in details, but I had referred to, we have FID detectors, we have thermo detectors, etc. We will talk about it in details in some next lecture. So you are going to have the detectors which are specific for the range of IR that you have selected. Now, photon detectors, when you talk about, it consists of thin layer of lead telluride or lead sulfide, which is supported on a glass, and it is enclosed in a evacuated glass envelope. That means something like a capsule, right? It is evacuated. There is no air allowed, and it is made up of lead sulfide, which is photoconductive cell, and it is sensitive to infrared, which is up to 3 microns. So it will absorb the signal, whatever is generated by the instrument, by the sample. I'm sorry, by the sample, and then it will be, if it is poor, you need to have magnifiers like photomultiplier tube will multiply the light signal received, and it will be multiplied so that the signal can be detected by the instrument. So here initially it is connected by the photo conductive cell, which is lead sulfide, and photoconductive is it allowing that light to come, and it is not stopping the light to come. Conductive, right? It is allowing that conductivity of or collection of that signal generated. And then if it is a strong signal, then it can be identified, or maybe it is multiplied using the multiplier systems like photomultiplier you have in UV visible, and then it will be detected and recorded. So if required, it will be amplified, that is multiplication I am saying, amplified, and then it will be measured. The conductance of light is uh, important. So the conducting material is required, and that is going to be the mm, should be working in the specific IR range. So for far IR, for mid IR, for near IR, you will be having a different collection systems or photoconducting materials that are used. Now, thermal detectors also are there, which are used in IR spectroscopy. So, if the radiation is above 1 micron, it can be detected by heating effects. So, thermocoupled, and you can just remember in two lines key, it is if the radiations are above 1 micron, you have to go with thermal detectors. And thermal detectors, they work on the method that heating effects, so that the resistance thermistors are there, thermocouple, what it is called as, which is going to sense that, and that signal is passed on to the galvanometer, a deflection is noted. So thermal detectors, to more details we will talk in UV visible also. Just 2 lines, 3 lines about thermal detectors here is more than enough. Now, as I said in the beginning, ki light source is going to be different. So mercury lamp, radium lamp, deuterium lamp, these things, yes, you understand. But what are the words? Nernst glower or glower source. That is 2 lines about it. The Nernst glower consists of a rod or a hollow tube, say about 2 centimeter long and 1 millimeter diameter. Now, what it is made up of? It is made up of a mixture of oxides of cerium, zirconium, thorium, and yttrium. So these are the metals. The metal complex is oxide complex is made, and that is going to act as the light source. So the nurse glower is non-conducting at room temperature. It is to be heated. So heating also, as we do the at home, the tungsten filament bulbs or tube lights, they get heated due to electric energy, and that is what is the light is generated. So similarly, you need to heat this by electric source, and then it will be subject to oxidation, and that will glow. So nurse glower is nothing but a small hollow tube consisting of the oxides of metals like cerium, zirconium, thorium, and yttrium. Now, another source that we have talked about is a Glober source. What it is silicon carbide rod, right? And it is going to be heated between 1300 to 1700 degrees Celsius. So neither at room temperature not at boiling water temperature it is going to heated, but it is going to be heated at a temperature between 1300 to 1700, and it will emit radiations in the IR region. So if you talk about tungsten filament light, the ordinary tungsten filament lamp is convenient source of near IR region, that is 4000 to 12800. So depending upon which region of IR you are interested to work in, you have to choose the light source. Now, when you are going to analyze, what kind of analysis we do. So the sample is placed, the IR radiation is falling onto it, sample is going to absorb it. What is going to be the output and how you are going to analyze that? So the thing is, you are going to plot a graph of percent transmittance rather than absorbance. So concentration versus absorbance, that is what we generally do. But here we are going to plot a graph of percent transmittance. All right. And the spectrum, like lambda max we calculate in UV visible, here the spectrum band or a peak will represent the absorption of infrared radiation. How it looks, we will see. Uh, these are the theoretical details. I'll just skip. I'll come on to the, yeah, schematic diagram. Now here, if you are able to see, you can see the range 4,000, 3,000, 2,000, like that, right? So are you able to see, this is percent transmittance? So when we say absorbance, it is 0.1 to absorbance 1, generally for normal colorimeters that we use, right? That is what we correlate the concentration versus absorbance and plot a graph. But zero point 0.1, when I say, it is 99% transmittance. 0.99 is transmitted. So percent transmittance is the other way of expressing. So either you express absorbance or you express transmittance. Here is percent transmittance. So out of 100% of light that was allowed to pass through the sample, how much is transmitted? That means how much is absorbed. So either you place absorbance or transmittance. Here transmittance is placed. So transmittance is always expressed as percent transmittance. And now you can see here the range 3,000 to 4,000. You are seeing a very broad band, right? Here also you are seeing a very broad band, but here you can see a single peak, right? So you are going to get these different types of peak sizes or band which is going to get generated, and they are going to be specific for specific molecule, functional group, specific bond, and what kind of bond um, activity has taken by absorbing the light, whether the bond stretching happened, whether the bending of the bond had happened. All these details also you can get to know. It is just to make you know how the graph is plotted. So here it is the wavelength that a region, IR region that you are scanning, and this is the percent transmittance is mm, marked. So when I say low absorbance, that means maximum transmittance. So here it is about 90% transmittance you are seeing. That means very low absorbance, right? And with such very small absorbance quantities, they become difficult to analyze. So it is converted to transmittance. So the picture is much clear when you are analyzing. So in the graph, what you are seeing the peaks, right? Sharp peaks or band of peaks, or there is, yeah, there is a very gap, right? So this is called as dip. So either you get the peak or you are getting a dip, right? So this is the area when there is no transmittance as such, zero transmittance. Fine. So these are just to make you understand the concepts. Now let's go to the certain examples, right? For example, if I take carbonyl group, where is it present? In all biomolecules, you get across this carbonyl carbons, COOH, right? So, or hydroxy region, right? So they are going to